Okay, our next problem goes as follows. 24.3 grams of magnesium is burned in 16 grams of oxygen gas. 40.3 grams of magnesium oxide is formed from this reaction. If 24.3 grams of magnesium is burned in 80 grams of oxygen gas, and then we have several parts to this problem. The first one is, what is the total mass of the substances present after this reaction? So there's a lot of numbers here, but really you have to take it one step at a time. First thing we know is 24.3 grams of magnesium, we burn it in 16 grams of oxygen, and we get 40.3 grams of magnesium oxide. All right, but if we turn around and we take the same exact amount of magnesium, 24.3 grams, and we flood the chamber with a lot more oxygen, 80 more grams of oxygen, first part is, what is the total mass of the substances present after the reaction? The second reaction with 80 grams. So it's really a law of conservation of mass thing, but the first thing you should just sort of think about is if we have 24.3 grams of magnesium, Mg is magnesium, and we add to that the amount of oxygen that was in the chamber before, which is 80 grams of oxygen, then the question is, what is the total mass of the substances after the chemical reaction? So we just add them together. 24.3 plus 80 is going to give me 104.3 grams after. Now, of course, some of this magnesium is going to combine with some of that oxygen to give me magnesium oxide, but there's going to be a whole lot of extra oxygen left over because our problem actually said 24.3 grams of magnesium burns with 16 grams of oxygen, giving us 40.3 grams of magnesium oxide. But if we take the same exact amount of magnesium and just put it with more oxygen in the chamber, we're probably not going to form any more magnesium oxide because really we have a fixed amount of magnesium. So we might put 100 tons of oxygen in the container, but once we run out of magnesium to react with, the reaction stops producing anything new. And that's what kind of happens here. We start off with 24.3 grams of magnesium, we burn it in 80 grams of oxygen, but to find the mass of the substances total after the reaction still obeys the law of conservation of mass, so we just add them together. Now our second question is, what mass of magnesium oxide is formed? What mass of magnesium oxide is formed? And I think you can see, you can use a little bit of logic here to sort of think about this. If we started with 24.3 grams initially, and we burned it with 16 grams of oxygen, and we only formed 40.3 grams of magnesium oxide, we used up everything. What do you think is going to happen if we start out with the same amount of magnesium metal and just flood the chamber with oxygen and react it again? Well, all that magnesium is going to be converted to magnesium oxide. There's going to be a lot of extra oxygen left, but how much magnesium oxide do you think is really going to be produced? Well, it should be, just by thinking about it, make exactly the same amount. Because this is sort of a question in testing your understanding of the principles here. If I take, it's kind of like thinking of a match, right? If I take a match and I have it inside of a jar, right? And I let that match burn, and then that match goes out inside the jar, and then smoke comes off of that match. So that's sort of like a chemical reaction. The smoke is part of the process, and you have some smoke filling the jar, okay? Now, what if I remove the jar? And so now I have a whole room full of oxygen, and I burn that match again, and I let it go out, and some smoke is produced. Now, how much smoke do you think is going to be produced in the second reaction compared to the first? Should be exactly the same amount, assuming there is enough oxygen in that jar to begin with. So it's sort of an exercise in understanding the idea that chemical elements come together to produce the products. If I burn that match in the jar, it's going to produce the same amount of smoke, because once the oxygen is combined enough with the sulfur on the match tip, then it's going to produce however much it's going to produce. Now, if I flood it with a billion tons of oxygen in the room, then the match is going to be using up as much as it's going to need to completely react. But once it's done, it's done. It doesn't keep reacting with oxygen, because once the material is done reacting, it's over. So if we start with the same amount of mass in both cases, we should produce exactly the same amount of magnesium oxide. But to be a little bit more mathematical about it, like on an exam, you might want to do something a little bit more involving our ratios and our proportions that we've been talking about. So we'll do that here. For part B, we'll just sort of just go through the motions to make sure that everybody understands. What we know is that for this reaction, for the very first reaction that was given to us, we know that 24.3 grams of magnesium combines with 16 grams of oxygen. And we know that that produces, so I'm going to put an arrow for produces or yields, 40.3 grams of magnesium oxide. Okay? So we know that this guy is reacting, giving us the magnesium oxide. All right, so what can we do? We can find the ratio of oxygen combining with magnesium. And that's going to help us predict, to do it a little more mathematically, how much is going to be produced in this case as well. So the ratio of magnesium to oxygen needed in this reaction is 24.3 grams of magnesium combining with 16 grams of oxygen in this reaction. And so what this is going to be, when I do this division, 24.3 divided by 16 is going to give me 1.52 grams of magnesium for every 1 gram of oxygen. So make sure you understand what's happening here. All I did was take the 24.3 divided by the 16. Another way to think about it, if you want to think of it this way, this is a fraction, like any fraction. I can divide the top and bottom by anything I want. So if I divide the bottom by 16, I'm going to get 1. If I divide the top by 16, I'm going to get this. So it's 1.52 grams of magnesium for every 1 gram of oxygen. So another way to write this is exactly the same thing, is 1 to 1.52. And the 1 goes with the oxygen, and this goes with the magnesium. So 1 gram of oxygen combines with every 1.52 grams of magnesium. So we now have this ratio, which is going to help us to do what we want, because the problem says if 24.3 grams of magnesium is burned with 80 grams of oxygen, what is the mass of magnesium oxide that's formed? What is the mass of magnesium oxide that's formed? So if I start with 24.3 grams of magnesium, right? And I know the ratio of how much oxygen is going to combine with that magnesium. Let me go ahead and make this a little bit more explicit. Magnesium. So we know what we're talking about. I know that 1.52 grams of magnesium combines with 1 gram of oxygen. So this unit cancels with this unit. So I've set it up so that the grams of magnesium cancel with the grams of magnesium. So when I do the multiplication, 24.3 times 1 divided by 1.52, the answer I'm going to get is going to be 16 grams of oxygen used up. And notice, this 16 grams of oxygen was exactly what we talked about in the first part of the problem. So what we've really done is kind of come full circle back to the beginning. The beginning of the problem told us that 24.3 grams of magnesium reacts with 16 grams of oxygen to make the product 40.3 grams. The second part, we said, okay, well, we'll look at the ratios. We'll figure out what the ratio of magnesium and oxygen is, and we'll apply it to the 24.3, and we'll verify that 16 grams really is used up. So we're kind of going a little bit in a mathematical circle just to prove to ourselves that the reactants, or the products, right, the amount of magnesium dioxide in this case is 24.3 grams of magnesium plus 16 grams of oxygen equals, and when you add these guys together, you'll get 40.3 grams of magnesium oxide. And that's the answer. And that's, if you remember, exactly what we said we probably should get just by thinking about the problem. Because the first reaction proceeded, gave us 40.3 grams. The only thing we did different was add a ton more oxygen. Excess oxygen, if you might think of it that way. So that's just the other oxygen that we added at the end doesn't really affect the chemical reaction, is really the point of this problem. You might look at this and say, well, what's the point of this? It's because to make sure you understand that if you just hold one reactant fixed, if you know what the reaction is going to require in terms of oxygen, 16 grams, and then if you just dump a ton of additional oxygen in there, it's not going to do anything. It's just going to sit there and float around unreacted, just like the match. Match burns out, rest of the oxygen hangs around the room because the limiting guy in this case is the magnesium. Once it's used up, it's not going to do anything else, okay? So that's the most important thing. Now the third part of the problem is actually a lot more interesting. The third part says if 48.6 grams of magnesium is burned, again in 80 grams of oxygen atmosphere, what mass of magnesium oxide is formed in that case? So this next part is really different because now we have changed the amount of magnesium that we start with. We start with 48.6 grams. So let's apply exactly the same thing. So for part C, we start with 48.6 grams of magnesium. But again, we've done all the work because we figured out from part B what is the ratio of oxygen to magnesium required for this reaction. So we use the exact same conversion factor. 1 gram of magnesium, actually, it's not 1 gram of magnesium, it is 1.52 grams of magnesium for every 1 gram of oxygen. That is the ratio. We're doing exactly the same thing we did before, we're just changing how much magnesium we start with. So this unit cancels with this unit. The units we're left with is how much oxygen we're actually going to use. So if we take 48.6, multiply it by 1, divide by 1.52, then the answer we're going to get is going to be 32.0 grams of oxygen used. Now think about this for a second. In this reaction, when we start with 24.3 grams of magnesium, we used 16 grams of oxygen to form the products. In this case, we actually, I didn't tell you this at first, but this is exactly double. We doubled the amount of magnesium that we started with, and it turns out that we require exactly double the amount of oxygen to make it react. That makes total sense. If you start off with, in this case, it's magnesium oxide, 1 atom to 1 atom, then if you double the amount of magnesium, you should double the amount of oxygen required. In this particular case, since it's 1 to 1, MgO, it's 1 atom of magnesium to 1 atom of oxygen. Okay? So in order to find out how much product we have, we just add these numbers together here. How much magnesium and how much oxygen. So we have 48.6 grams of magnesium plus the 32 grams of oxygen. And that's going to equal, we do 48.6 plus 32 is 80.6 grams of magnesium oxide, which is the product, 80.6 grams. So in other words, we doubled everything, so the amount of product that we get is double from the other case. And that was sort of the point with this. So again, you know, none of the math here is very difficult when you look at it. I mean, you're doing division, multiplication, addition. I mean, as far as mathematical skills, none of these problems are really difficult. The challenge is knowing what to do. That's always the challenge. So as we work through these problems, make sure you're really taking the time to understand the thought process behind it, because if you don't, then you're missing 99% of the reason that we're doing these problems, to build your skills and build your confidence. Okay, our final problem says 1 oxide of nitrogen has an oxygen to nitrogen mass ratio of 1.142 to 1. Which of the following oxygen to nitrogen mass ratios are possible for other oxides of nitrogen? And so I'll write those on the board. We have a few different choices. We have 0.571 to 1. We have 1.000 to 1. We have 2.284 to 1, and we have 2.500 to 1. Make sure you understand what I'm asking you here. This is an oxygen to nitrogen mass ratio. So for instance, in this case, let's look at the original problem. An oxide of nitrogen, the oxide of nitrogen that we're talking about initially has 1.142 grams of oxygen to 1 gram of nitrogen. This is the original one that we're talking about in the problem. So for every 1.142 grams of oxygen, this is how much nitrogen is present in the molecule. And so what we're trying to do is predict for other oxides of nitrogen. For other oxides of nitrogen, you got to really understand what that means. That means other chemical compounds that involve nitrogen and oxygen, but maybe not in the same ratio. Think about carbon monoxide, CO, and think about carbon dioxide, CO2. Those both contain carbon and oxygen, but different numbers, different amounts of molecules combining in for each molecule. Another one is hydrogen peroxide, H2O2, is really the same elements as water, H2O, right? But remember, we did talk about a law that involves that and that predicts and kind of gives us a little bit of help, and that's the law of multiple proportions. We talked about that in the last section. What it basically says is if we have two different compounds with the same elements, right, that the mass ratios on each of these guys is going to be related by some kind of multiple. So here we know the mass ratio of the original compound that we have. This is the mass ratio here. And the question is, which of these compounds could possibly be another oxide of nitrogen? And so you have to use the law of multiple proportions and realize that the only way any of these guys is going to be even a possibility using the law of multiple proportions is if these ratios are some sort of nice multiple of what I have here. And so if that isn't quite clear, go back and watch a section on law of multiple proportions. That is the reason why. So given this information, the only criteria that we would know that one of these guys could possibly be another oxide of nitrogen, in other words, another compound that contains oxygen and nitrogen only, is if these ratios are a nice sort of multiple of this guy here. So what I mean by that is, let's think about this for a second. This is 1 gram of nitrogen to 1 gram of oxygen. So what if I take 1.142 and multiply it by 2? What am I going to get? This guy multiplied by 2. I'm going to get 2.284. 2.284. So if I look up in my list, I'll see right away I do have another candidate, 1 gram of nitrogen to 2.284 grams of oxygen. So this is actually one of the valid oxides, because this mass ratio here is really a multiple of this one. So this is 1 gram of nitrogen to 1.142 grams of oxygen. This is 1 gram of nitrogen to 2.284 grams. So it's kind of like requires double the amount of oxygen for every single unit of nitrogen there. So that's why this is sort of like a multiple, because it requires double the oxygen for the same amount of nitrogen. Okay, let's keep going. What if I have 1.142? What if I multiply by 3 to try to get another multiple? I'm going to get 3.426. And I don't see anything up here with 3.426. If I keep going higher, 4, 5, 6, 7, I'm going to get higher and higher numbers, so I'm not going to really make any progress. So let's go the other way. 1.142, what if I multiply by a half? Which is a nice kind of round number. I'll get 0.571. And I see that I do have this guy here. So this is another valid guy, because my original oxide is 1 gram of nitrogen to 1.142 grams of oxygen. This one requires half the amount of oxygen. So basically, this is sort of my original compound. This requires double the amount of oxygen for the same amount of nitrogen. This one requires half the amount of oxygen for the same amount of nitrogen. These guys are not any sort of multiple of any number I have in this problem. So they really, according to the law of definite proportions, or law of multiple proportions, they really aren't related. So they're kind of cast out. And if that, hopefully that makes sense to you. If you need to go back and review the material and the examples that we gave on law of multiple proportions, go ahead and do that. But I think you can kind of see that the fact that this is double and this is half is really just because the actual molecule may have an extra oxygen atom in there, or maybe half as much as oxygen atom of the original molecule. So if we knew the actual chemical makeup and the actual compounds, we could show this to be true, but that wasn't the point of this problem. The point was to use the law of multiple proportions to predict ahead of time which of these guys could be candidate oxides of the nitrogen there. Okay, so we're done with this section. We worked quite a few problems. I tried to solve problems for you that are going to really flex our muscles on the law or the atomic theory of matter, which is really a huge subject dealing with law of conservation of mass, how atoms combine to form compounds, how the mass percentages are constant for different samples, law of multiple proportions, and on and on. And so I also tried to demonstrate that a lot of these problems, they're not going to hold your hand and they're not going to tell you, hey, go ahead and use the law of conservation of mass to solve this problem. It's just never going to be done. So read the problem, know your laws, and apply them yourself, and know when to apply them yourself. And that's one of the reasons why chemistry seems to be difficult for a lot of people, but with practice, you'll get confidence. So I urge you to work these problems yourself if you think you need to. Definitely open up your book, practice problems from your own textbook that you're using in class, get your confidence going, and make sure you understand these foundational topics because they're going to come back and they're going to be used over and over again as we go through this course and as you go through your chemistry class.